Alright guys, so today we'll be doing a pre-lab video for Lab 2, Introduction to Stereonets. Before we start this video and get into stereonets, I'd just like to go over how this lab will relate to our field trip last Friday to Ben Burton Park. So at Ben Burton Park, remember we were using our Breton compasses to take the strike and dibs bedding planes, which are both joints, fractures, as well as foliation. So today we're going to learn how do we put those bedding planes as well as lineations, which we'll talk about later, into a format where we can run analyses on them to solve a geologic problem or find trends in the data. So first, let's go over strike and dip. So here we have an inclined plane where this plane has been lifted up a length L, which you can see here, which is same on both sides. Across that plane we have strike, which runs parallel at an even elevation, and 90 degrees to that we have dip. So if we pull that out, we have a elevation to our plane. Our plane comes down at a diagonal, and with a horizontal plane across the top, we have our dip angle as well as dip direction. So what we'll be doing today is using that strike and dip to plot planes in a stereonet. So moving on, we are going to imagine our plane in 3D space. So here's our plane that we were just talking about. It has some orientation to where it has a strike and dip. Remember, say the plane is oriented like this. Our strike is going to be somewhere like here. 90 degrees of that is dip. And remember, if you're ever in the field and you are having a hard time figuring out dip, pour some water on it. It'll take the fastest route down. That is your dip and dip direction. So moving on to taking our planes and putting them into a stereonet form or a stereonet format. We have our plane here. Once again, remember it's dipping at some angle. We want to try to visualize this in 3D, put it into a stereonet, and then be able to analyze the plane in 2D. So what we'll do is we'll have a bowl like this, and if you can imagine, this bowl has a north, south, east, and west. We know that the way this plane is oriented, it should fit within those coordinates. So if we were to have a plane that was striking north-south, so striking north to south, that plane should fit in here. Say that plane had a dip of 90 degrees vertical, that'd be represented by this plane in this bowl right here. Say that dip was horizontal or 0. This plane would still be oriented like this, and it would be horizontal. We can do the same if it was striking a different way. Say it was striking east-west. Say the plane was dipping 90 degrees. That plane would fit in vertical east-west as it did north-south. So if we were visualizing this and you had multiple planes, you could see how planes would be oriented in many different orientations. And so what this is kind of visualizing is we're taking this from 3D, and when we work with stereonets, we're going to be looking at it in 2D. So what does that mean? If we take our plane and put it back north-south, like so, with a vertical dip, there's two things you want to realize. You want to realize that it's still striking 0 to 180, but you also want to realize and visualize what this would look like if we were looking at the top. So if I was to rotate this towards the camera and we are just looking at the top of the bowl now, you can see that we have a circle and we have a line. So remember, in 3D space we have a plane. If you transform that space to 2D space, we have a line. So our plane, which was in 3D, has now become a line in 2D when we look directly at the center of this bowl. Remember, it has a vertical dip, so it's just a straight line from north to south. But if you change that dip in any way, say you make it about 45 degrees, you can see where there is now an arcuate shape in the back of the bowl representing our 2D line if this was on a stereonet, and you can follow it all the way back here. And then again, if you follow the line that the plane is making with the back of the bowl and you keep rotating it up, what's happening? Well, our dip is getting shallower and shallower until it's horizontal. And it'll be important once we start working on stereonets to come back to this so you can start visualizing, some of these different orientations that we're going to be working with. And once again, this plane can be oriented, or now line, since we're in 2D space, can be oriented any which way. So again, if your line was striking some angle into the northeast and some angle into the southwest, but it's still vertical, it's represented the same way. Striking northeast, striking southwest, vertical dip. It's a straight line across. And then if we put it back into 3D, we can see that our plane is vertical and it's striking northeast to southwest. The next lesson into this is figuring out, okay, what if we have a bunch of these planes in here? If you do field work of any sort, you need to have, hundreds to thousands of measurements. The problem you're going to run into is putting 100 to thousands of planes into a stereonet. It's going to fill up pretty quick. So there's a way that we use another stereonet tool to kind of take care of a whole bunch of data, and this is what we call polls. So a poll, let's take this out for a second. Here's our plane. A poll is just a line in 3D space. Remember that we're in 3D space right now. A poll is a line. A poll is going to be 90 degrees that's all right, 90 degrees from our it'll make a 90-degree angle with our plane. So why would we do this? Why are we adding this pull on? Well, if we think about this again, in 3D space we have a plane and we also have a line marking the pole. If we move this plane and line into 2D space, we go from a plane to a line and a line to a point. So if you have a whole bunch of data on your stereonet, it's a lot easier to recognize trends in that data, figure out your geologic problems if you have a whole bunch of points compared to a whole bunch of lines, which would be our planes. And this will make more sense as we move into the stereonet. You may have to come back and revisit this part. It's just an easy way to visualize this.